Chemical bonds are the glue that holds everything together, giving rise to an incredible diversity of substances from a relatively small number of chemical elements. But these bonds aren't static, they're constantly rearranging, and it's this rearrangement that allows important processes like respiration. Breathe in oxygen, breathe out carbon dioxide, and our oxygens have picked up a carbon. Usually this isn't too difficult. The glue holding our atoms together is more like the paste we use in art projects as kids. But for some of the world's most important molecules, things like carbon dioxide, carbon monoxide, nitrogen gas, the bonds are incredibly strong. We've traded in our paste for superglue. If we want to do anything with these molecules, like take the greenhouse gas carbon dioxide and transform it into a usable fuel, we need a new strategy. We need some way to pull apart the superglue. We could try to copy nature, which has developed some elegant schemes for doing this with a limited palette of chemical elements. But the enzymes that the natural world uses contain thousands of atoms in complicated arrangements, not a feat we can replicate in the lab. At Carleton College, I work with a team of undergraduates on a different approach. We have a trick up our sleeves that nature doesn't, because we have access to the entire periodic table. We work like architects, designing simple chemical structures with combinations of two elements that don't usually play nicely together. Then we build those structures through chemical synthesis in the lab. Our goal is to find combinations where those elements can cooperate to perform a reaction that they couldn't pull off separately. Sort of like if two people are working to move a heavy object, one person pushes, the other pulls. For instance, we have recently shown that two very abundant elements, cobalt and silicon, can be combined through an unusual double bond to break the strong carbon-oxygen bond in carbon dioxide, making carbon monoxide, which can be turned into fuel, and an oxygen atom that we hope to transform into water or oxygen gas. With the whole periodic table at our disposal, the possibilities for tackling this superglue problem are nearly endless.